Early in the 20th century, a very clever experiment was done to determine how fatty acids are degraded. Recall from earlier that radioactive elements can be incorporated into biological molecules and followed through the body. A German biochemist, Franz Knoop, devised a similar kind of labeling experiment long before radioactive tracers were available. Knoop fed dogs fatty acids in which the usual terminal methyl group had a phenyl group attached to it. Such molecules are called omega-labeled fatty acids. When he isolated the metabolized fatty acids from the urine of the dogs, he found that phenylacetate was formed when the fatty acid had an even number of carbon atoms in the chain. But benzoate was formed when the fatty acid had an odd number of carbon atoms. Knoop interpreted these data to mean that the degradation of fatty acids occurs by the removal of two carbon acetate groups from the carboxyl end of the fatty acid. We now know that the two carbon fragments produced from the degradation of the fatty acids are not acetate, but acetyl coenzyme A. The pathway for the breakdown of fatty acids into acetyl coenzyme A is called beta-oxidation. The beta-oxidation cycle consists of a set of 4 reactions whose overall form is similar to the last 4 reactions of the citric acid cycle. Each trip through the sequence of reactions releases acetyl coenzyme A and returns a fatty acyl coenzyme A molecule that has 2 fewer carbons. Reduced coenzymes are also produced. 1 molecule of FADH2 equivalent to 2 ATP molecules and 1 molecule of NADH equivalent to 3 ATP molecules are produced for each cycle of beta oxidation. The enzymes that catalyze the beta oxidation of fatty acids are located in the matrix space of the mitochondria. Special transport mechanisms are required to bring fatty acid molecules into the mitochondrial matrix. Once inside, the fatty acids are degraded by the reactions of beta oxidation. As we will see, these reactions interact with the oxidative phosphorylation in the citric acid cycle to produce ATP. The first step is an activation reaction that results in the production of a fatty acyl coenzyme A molecule. A thioester bond is formed between coenzyme A and the fatty acid. This reaction requires energy in the form of ATP, which is cleaved to AMP and pyrophosphate. This involves hydrolysis of 2 phosphoanhydride bonds. Here, again, we see the need to invest a small amount of energy so that a much greater amount of energy can be harvested later in the pathway. Coenzyme A is also required for this step. The product, a fatty acyl coenzyme A, has a high energy thioester bond between the fatty acid and coenzyme A. Acyl coenzyme A ligase, which catalyzes this reaction, is located in the outer membrane of the mitochondria. The mechanism that brings the fatty acyl coenzyme A into the mitochondrial matrix involves a carrier molecule called L-carnitine. The mechanism that brings the fatty acyl coenzyme A into the mitochondrial matrix involves a carrier molecule called L-carnitine. The first step, catalyzed by the enzyme carnitine acyltransferase 1, is the transfer of the fatty acyl group to carnitine, producing acylcarnitine and coenzyme A. Next, a carrier protein located in the mitochondrial inner membrane transfers the acylcarnitine into the mitochondrial matrix. There, carnitine acyltransferase 2 catalyzes the regeneration of fatty acyl coenzyme A, which now becomes involved in the remaining reactions of beta oxidation. The next reaction is an oxidation reaction that removes a pair of hydrogen atoms from the fatty acid. These are used to reduce FAD to produce FADH2. The dehydrogenation reaction is catalyzed by the enzyme acyl coenzyme A dehydrogenase and results in the formation of a carbon-carbon double bond. Oxidative phosphorylation yields 2 ATP molecules for each molecule of FADH2 produced by this oxidation reduction reaction. The third reaction involves the hydration of the double bond produced in reaction 2. As a result, the beta carbon is hydroxylated. This reaction is catalyzed by the enzyme enoyl coenzyme A hydrase. In this oxidation reaction, reaction 4, the hydroxyl group of the beta carbon is now dehydrogenated. NAD+ is reduced to form NADH that is subsequently used to produce 3 ATP molecules by oxidative phosphorylation. L-beta-hydroxyacyl coenzyme A dehydrogenase catalyzes this reaction. The final reaction, catalyzed by the enzyme thiolase, is the cleavage that releases acetyl coenzyme A. This is accomplished by thiolysis, attack of a molecule of coenzyme A on the beta carbon. The result is the release of acetyl coenzyme A and a fatty acyl coenzyme A that is 2 carbons shorter than the beginning fatty acid. The shortened fatty acyl coenzyme A is further oxidized by cycling through reactions 2 to 5 until the fatty acid carbon chain is completely degraded to acetyl coenzyme A. The acetyl coenzyme A produced by beta oxidation of fatty acids then enters the reactions of the citric acid cycle. Of course, this eventually results in the production of 12 ATP molecules per molecule of acetyl coenzyme A released during beta oxidation. As an example of the energy yield from beta oxidation, the balance sheet for ATP production when the 16-carbon fatty acid palmitic acid is degraded by beta oxidation is shown here. Complete oxidation of palmitate results in the production of 129 molecules of ATP, 3.5 times more energy than results from the complete oxidation of an equivalent amount of glucose. So if we draw palmitic acid, which is a 16-carbon molecule, if we draw it out in the bond line structure, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. A question that is commonly asked is how many times can beta oxidation occur based off of the number of carbon atoms? Well, then the question becomes, how many 2-carbon units can I split this up into? Now, this molecule has 16 carbons, so it might be a knee-jerk reaction to say, well, 16 divided by 2, I can do it 8 times. But this is not true. If you look at how many times you can cut this up into 2-carbon units, 1, 2, 3, 4, 5, 6, 7. So you can split this molecule up into 7 2-carbon units to produce 8 molecules of acetyl coenzyme A. But you're only doing the beta oxidation process 7 times, and that is why you produce 7 molecules of FADH2 and 7 molecules of NADH. Therefore, from the beta oxidation itself, since FADH2 is worth 2 ATPs, 7 times 2 gives you 14, and NADH is worth 3 ATPs, 7 times 3 gives you a total of 21. Now, each one of those acetyl coenzyme A molecules can enter into the citric acid cycle. And since we have 8 of those molecules, the citric acid cycle produces 3 molecules of NADH, 1 molecule of FADH2, and 1 molecule of ATP. But again, we have 8 acetyl coenzyme A molecules. And thus, in the 8 turns of the citric acid cycle, we produce 8 times 3 NADHs. 8 times 3 is 24, but each one of those NADHs has a value of 3 ATPs. So 24 times 3 gives you 72 ATPs. Again, we do 8 turns and we produce 1 FADH2 each time. So 8 times 1 gives me 8, but each FADH2 is worth 2 ATPs. Therefore, 8 times 2 gives me a total of 16 ATPs. And then finally, the GTP is worth 1 ATP, and we have 8 turns. Therefore, we form 8 ATP molecules. Therefore, when you tally up the 14 ATPs, the 21 ATPs, 72, 16, and then the 8 ATPs over here, when we tally all that up, we get 131 ATPs. The cost was 2 high-energy phosphate bonds, which cost us a total of 2 ATPs. So we take 131, subtract 2, and we get a net ATP production of 129 ATPs. The summary is also shown here.